So welcome to the Unit 4B review, Ohm's Law, circuits, that kind of stuff. You can see on the paper that I have right in front of me on the screen, just a couple of things to keep in mind. Really just a lot of what I'm going to say, a lot of the note card suggestions here, just that's the main bit of this. That's the main thing on this, this unit. So before I really get going though, I'm going to be glancing around every once in a while. I'm going to be looking in that direction to look at my phone to see if anybody uses the Remind app to ask me questions. I'm looking in that direction every once in a while to see if anybody has questions in the chat or if anybody's misbehaving. Auto moderator should hopefully take care of anything really egregious. But what I have on the paper right now is just some suggestions to write in your note card, and we will take care of that in class tomorrow on Wednesday if you don't take care of it before that. But basically just a couple suggestions. This unit does focus on Ohm's Law, the relationship between voltage, current, and resistance, and also simple basic circuits. So essentially just what is a circuit, what does a battery do, and parallel circuits versus series circuits, that kind of stuff. So like it says here, some note card suggestions. Make sure you understand what the variables are. So that's going to be a big one. The names of the variables, in other words, voltage, current, and resistance. The symbols. So what's just, V for voltage, I for current, and R for resistance. Make sure you know the units, volts for voltage, and then the unit symbols too. So V for voltage, volts, current, and this is going to be, I'm going to go through this in the review, but current is going to be I, and the unit is amps, which is capital A, and then resistance R in ohms, which is that Greek letter omega, the upside down, well, U thing with the things, Greek letter. And also on your equation or your note card, you're going to want to have the equation. You can have it as V equals I times R. You can have all the different varieties of the arrangements of that. You should be able to do the algebra to rearrange it for anything, but you got to make sure, when do you multiply, when do you divide, and how do these things relate. If you're comfortable or you're more comfortable using the triangle trick, please be my guest. Remember, for the triangle trick, you cover up whatever you're trying to solve for, whatever you need. So if you're given voltage and current and you need to solve for resistance, well, you just cover up resistance, and now you know you have to take V divided by I. Or if you have voltage, or you're trying to solve for voltage, and you have current and resistance, then you cover up voltage and you multiply, just like that. Make sure you're familiar with the schematic diagram symbols. The ones on the review are pretty good, and make sure you know how to draw them. Straight lines, use a straight edge of some sort when you draw your schematic diagrams, your circuit diagrams, and get some practice with that from the review. Make sure you understand series versus parallel circuits. So without further ado, I'm going to get to the review guide. Okay, so come back to the beginning and you can check out the note card suggestions. Also, it is on the OneNote already, so if you want to just check out the OneNote, I have suggestions there as well. Add whatever you want, whatever you can fit on that note card. It's fair game. Alrighty, so this is probably why you're here. So we got our review guide here. This is pretty much what you need to know for the test. You're going to be tested on it. It's like usual. It's not going to be, here's a problem you have to solve. It's going to be a situation, and you have to use what you know to solve the situation. So I guess I'm just going to go through and answer these. Voltage. Voltage causes a current, and that's what you need to get a current. Is you've got the voltage, which is the electrical pressure, or as I say here, the pusher. It's a pusher, so it's causing pressure, and it's going to cause that current. It's going to cause the flow of electrons. Okay, it's going to cause the electrons to move. It causes current. It causes those electrons to move. Voltage sources, there's a million of them, but battery is the big one. You could also put like a an outlet in the wall. So just there's lots and lots of things. I'm not going to write the second one. You could come up with something. Symbol for voltage, V. The unit for voltage is volts. And also, I guess we could put in parentheses V. So make sure you're familiar with that. The symbol in the unit is the same. So it could be slightly confusing because the others are not like that. But just be aware of that. So that's voltage. Voltage causes the pressure. It's the push. It's necessary for current. And without it, this is what the battery does, by the way. It's all the battery does. The battery only pushes. It doesn't supply charges. It pushes the charges that are already there. Current. It's the flow of, and I'll take charges. I'll take electrons, charges, or electrons. And within a conductor, and this is a little funny worded. I probably could have worded this a little bit better, but basically within a conductor or like a wire or a piece of metal or anything like that. So that's why there's so much room, I guess, is just to give you an opportunity to write all these different things. Charge will only flow if there's a voltage source. Well, this typo, I apologize. This is true. Okay, make sure you know that. Without that, without a voltage source, without a pressure, you're not going to get any kind of flow. The symbol for current is a capital I. The unit for current is amps or a capital A. Okay, that's amps. All right. It's just basic fundamentals for this this unit. So making sure you're familiar with the basics. Resistance. Make sure I got that on the screen there. Oh, I'll go a little slower. Okay. Resistance, by the way, message me, use the Remind app, use the chat if you have questions. Tell me to slow down, whatever you need me to do. So resistance is resistance or opposition to, and that you might need to write that in there because that wasn't in the original. I added that because that's what it is. So what is it in resistance, or what is it in opposition to? It's in opposition to current. It slows it down. It doesn't block it, but it slows it down. It squeezes it tight. So the symbol for resistance is a capital R. The unit for resistance is that ohms. And this is where you're going to have that Greek letter omega. All right. So that's the fundamentals. That's the basics. You absolutely have to know this stuff. If you don't know this stuff, you are going to have a very bad time. And I don't know what you've been doing the last last week or two. Because, well, I mean, you just got to know that. That's just it. That's the basics for electricity. So if the voltage and a current, now there's a lot of ways that we can answer this question. Basically, the gist of it is if the voltage increases, that is a terrible choice of colors. I will not use that again. Let's go purple. So if it increases, then the current will increase. All right. If the voltage decreases, then the current will decrease. In the key, I think I might have written it, if it doubles, then the voltage, if the voltage doubles, the current doubles. It's saying the same thing. It's just the specific. If the current is cut in, if the voltage is cut in half, then the current's going to be cut in half. It's like literally whatever happens to voltage happens to current. And that's why this is called a direct relationship. Direct meaning whatever happens to voltage happens to current. So if you push twice as hard, you're going to get twice the current. You're going to get twice as much flow, twice as much movement. All right. So that's that. I don't like that color. I don't want to be messing around too much with these colors. So resistance and current. Again, this is a little bit different down here. So for resistance and current, if the resistance increases, then the current will decrease. In other words, if you get more resistance, you're going to have less current. If the resistance in a circuit decreases, then the current is going to increase. If one goes up, the other one goes down, basically. I should say if voltage if resistance goes up, the current is going to go down. The current does not affect, it doesn't go both ways. It doesn't, like if you change the, how do I say this? You can't change the current to change the resistance. It doesn't work out like that. If you change the resistance, you could change the current. And since when resistance goes up and current goes down, and you know the opposite is true, this is what we call inverse relationship. In other words, an inverse relationship is one goes up, the other one goes down. That's all that means. All right. So not seeing any questions. We're just kind of flying through this. This is the basics of this. I mean, I guess, well, not really basics, but it's definitely all the important stuff that you need to know about this. I guess this is all the basics. It's all important. So that's the relationship between voltage, current, voltage, and resistance, or I should say resistance and current. Moving on, we're going to get into actually the actual equation here. And so to when we look at Ohm's law, we label the variables. Well, this is going to be voltage, of course, because of the V. This will be current, that capital I, and the R is going to be, of course, resistance. So current's the only one that kind of plays funny there. The other one, you got a V is V, and the R is R, and then, you know, C is I don't know. So that's what you need to know from that. Make sure you can do that. All right, that's like the only thing. So here we go. We have an example. I'm going to switch to pencil because that's math and I don't want to mess it up. Or rather, if I do mess it up, I want to be able to change it. So in my example, I have I is equal to 4 amps. I have resistance is 500 ohms. And we need to find volts. I'm sorry, yeah, we need to find volts. So I did my first step. I listed the knowns and the unknown. I listed the givens and the unknown. And now I'm going to use my equation, V equals I times R. And if I need to rearrange it, I do, but it turns out that I think this is going to work out fine. If I was using the triangle method, I would cover up the V, and I would see that I had to multiply I times R. So I'm going to do that, and I'm going to actually work this out. So 4 amps, 500 ohms, I multiplied those two things together, and make sure I'm still on the screen. So 4 times 500 is 2,000, and it's volts for the voltage. Okay, so you see how just being familiar with the letters and what they stand for is going to be tremendously helpful here. Being able to pick out which equation to use, which version of the equation to use. Tremendously helpful. In fact, not even just helpful, it's like required. You need to be able to do this. So moving on. No questions. That's fine. I hope this is going okay. So this is it. I mean, if you could do this, you know, be able to pick out this kind of stuff. You probably won't just be given I is 0.5 A and V. It might say the current is 0.5 A. It might say, you know, the voltage is. It might say the resistance is. So just be able to, like in some of the examples we've been doing in class. So once again, I'm going to list this out though, just to make sure that I have it and I don't want to mess this up, right? So I organize things to help me visualize it. It's like if I'm working on a project, if I'm working on making something, I'm going to take out all the tools I need. I'm going to make sure everything's arranged. If I'm cooking something in the kitchen, I'm going to get all the ingredients ready to go, sitting out on the counter and in a place where I know where to find them. I don't want to be halfway through something and realize I screwed up. Did I add the salt? Did I, you know, do I need to cut this piece? And oh, I had a remind, but it's not about this. So anyway, the point is I lay out all the stuff and that way I know I'm doing this correctly. So I have V equals I times R is the starting equation, but I don't want to solve for velocity. I don't want to solve for voltage. I want to solve for resistance. So I could use the triangle, and I'll just do the triangle because I know some of you guys like the triangle. It's not my favorite, but if I got this all set up, I might as well use it. So if I want to solve for resistance, I'm going to cover up the resistance, and I can see that resistance is, well, voltage is on top and current is on the bottom. So resistance is voltage divided by current, all right? because I covered up what I didn't want to find. Or I could just solve it algebraically. I divide both sides by I, and that leaves me with R is equal to V divided by I. Both ways are fine. All right, so volts was 220, and current is 0.5 amps. And so my resistance is 220 divided by 0.5, and so that should be 440 volts. Wow, not volts. See, this is why I do it in pencil. You want to be able to erase it. If you leave it as volts on the test, you just lost some credit there. You just lost some points. So that's resistance. So that's going to be ohms. All right, so make sure you get the correct units. All right, not seeing any chat, so that's fine. All right, so that's essentially the math, but of course it's a review, so there's going to be some repetition, and that's okay. So we've got a gnat flying around here, is trying to learn some physics. It's fine as long as it doesn't bother me. We got our voltage, and the symbol for voltage is V. The units is volts, and the symbol for the unit symbol is that V again. All right, we've kind of already been through this. So current, the symbol is I. This is kind of, by the way, is a nice little chart to put on your note card tomorrow. The unit is amps, amperes, capital A. Resistance is R, capital R for the symbol. The unit is ohms. Yeah, I already wrote all this stuff, but like I said, it's a review. I want to make sure the stuff goes into my head, and so I'm going to write this by hand onto my paper, because that is proven. It's been proven that is one of the best ways to learn something, is to write something out over and over and over again. Like it or not. I never liked it. I had to learn stuff the hard way. All right, I had to learn stuff. I had to learn that I was not as smart as I thought I was, and yet I was capable of doing stuff. And so writing stuff over and over again was helpful, but I didn't learn that until much later. Alrighty, schematic symbols. So draw the schematic symbol for each part. Now this is important. You gotta make sure you're aware of this stuff. If you want to include it on your note card, I suppose that's okay. In fact, it might be a good idea, but just remember that, yeah, we'll go 3. Every part has 2 connection points. So when you draw it, I do like to draw a little bit of the wire. Is that green not gonna work? Why do I keep picking up that green? Let's try a different color. So we can kind of see that okay though. So every side has everything has 2 different connection points. So I always draw 2 bits of the wire, just one on either side. All right. That way you always remember 2 points. All right, a resistor. And this goes vertically as well as horizontally, so I could turn those on its side if I want to. But I do try to be neat here, and I'm rushing a little bit, I'll be honest with you, so it didn't turn out very well. I don't really care how many peaks and valleys you have here. You could do 3 and 2 like I did. You could do whatever. I could do a couple. Don't get too carried away. Don't go too crazy with it. Light bulb, I mean, there's, as we've seen in class, there's 1.5 million symbols for a light bulb. You can use the one that I like because it's simple. There's a couple other ones, like a little curly Q with the little, it sort of resembles a lamp, an old-fashioned lamp. And there's probably a couple others that I just am not aware of, but these are the 2 that I use the most. And that's, you know, they're fine. A switch. You don't have to put these little dots like I got, but the dots are kind of helpful. They're not strictly necessary for us now. If you get into more detail later, if you go into this, I would say that you're going to want to include these little dots, because it just makes things so much cleaner and neater. And that's the whole point of a schematic diagram, is to clearly convey what you're trying to do. And a wire, well, I mean, straight line, use a straight edge. I got lucky right there. I did not use a straight edge. Don't tempt luck on a test, okay? Say that again. Don't tempt luck on a test. If you feel like, oh, I could probably draw a straight line, that's fine, but it's a test. So do you really want to risk it? I don't know if I would. All right. That said, I did not plan very well. I'm going to get out all right, this is a ruler, I guess. I don't know how old it is, but it works. So I'm also going to use a pencil for this. It says draw a circuit that shows a battery resistor and a light bulb connected in parallel. So parallel means you're going to have different pathways. You're not going to have it all in one thing. So watch what I mean by that. So a battery, a resistor, and a light bulb. So I'm going to need 1, 2, 3 things. So I'm just going to draw it. Let's make sure it's on the screen. And I'm going to draw the battery first. And I'm going to draw, oops, see, I already started. It's so tempting just to draw it without a ruler, without a straight edge. So I'm going to draw a little bit here. Just draw from there to there. And then I'm going to get my ruler set. I have no idea where that went. I need to lean a little bit. All right. I'm kind of doing this from a funny position, so apologize about that. But so now I need to connect those two together. If I just were to draw a straight line down, that would be a short circuit. It wouldn't work. It would cause a fire. So I want a resistor in here. So what I'm going to do, I'm going to give the electricity a pathway to get back to the battery. All right. So that works. And it says a light bulb, so I'm going to also draw a light bulb back. So I got a little extra wire here. I'm just going to erase it, clean that up a little bit. All right, fix my light bulb. All right, so essentially just remember this is what's going on. Parallel has extra pathways. So you come out of the battery and you could go down the pathway and you come to a choice. You come to a junction. You go either down through the resistor and back, or you can go all the way over to the light bulb and back down. Okay, that's the same thing. Now I'm going to draw this one really quickly without the straight edge, so I apologize about this. But one other way to do it is, there's a lot of other ways to do it. I could just draw like the resistor, that's horrible, one way and the light bulb the other way. It doesn't matter how you do it, because again, when the electricity leaves the light bulb, it has a choice. It could go one way or the other way, and that's the point of having a parallel. All right. Now in series, like I say in class, it's like watching a Netflix series. If you don't watch them in order, a lot of times they're not going to make sense, and so everything you have to watch all of them, and you have to watch them in order. So we want a battery, a switch, and a resistor, no light bulb this time, in series, which all that means is, and I'm just going to put the ruler away because I'm not taking a test right now, although I'm probably going to regret it. So I just want to be quick for you. I don't want to waste your time at this point. Use a ruler. So use a ruler. So in series, I'm going to draw a switch with my little symbol there for a switch, and it's series, so there's no choices, there's no breaks, there's no splits in the path. So it doesn't matter where you put this thing, as long as you're along the same path. I'm following the path. And now I need a resistor, and I go back to the battery. All right, so that's a series circuit. There's only one choice. It goes around and around. All right, as opposed to the other one where there's a choice. All right, so that's in series. All right, good. No questions. That's fine. All right, good. Hopefully it's just review, and this is just answering questions as I go. I'm trying to anticipate questions you might be having. Why'd that get blurry? Fix. Good. Okay. So we have a circuit containing one battery and one light bulb. The current blah, 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 blah. Oh, I probably shouldn't blah, blah, blah. I should actually probably be like, okay, I got 0.2 amps and a voltage of 6 volts. I need to draw a schematic picture for the circuit. Well, I've got one battery and one light bulb. So this is going to be a very simple circuit. Let's draw it this way this time, just to be different. So instead of going horizontal or vertical, we'll go horizontal. And once again, I'm going to try to draw straight. If I was doing this for a test or I want to be really careful, I would use a straight edge. But since I'm trying to do a quick demonstration of all this, it turned out pretty okay. That's it. Okay, we got our one battery and one light bulb. Calculate the resistance of the circuit. We're getting closer to like something now. You got to pick out stuff. So we want resistance. We know that the current is 0.2 amps. So I is 0.2 amps. We know that the voltage is, make sure it's on the screen, is 6 volts. and we want to know the resistance. So I've got my givens and my unknown, and I feel like I solved this one before for R. Hey, look, I did. So I know already because I've done this before, and this is what practice does. You start to see familiar patterns. So I know resistance is V over I, and so I don't even have to really do much in order to figure out that I have to divide. And so I do that. So I'm going to do voltage 6 volts divided by 0.2 amps, and that means that my resistance is 6 divided by 0.2. 6 divided by 2 would be 3, and so that's going to be 30 ohms. All right, probably I'm going to check that on my calculator, but I'm pretty sure that's what it is. Tell you what, I'm just going to double check my calculator. So 6 divided by 0.2, yeah, 30. Okay, good. All right. Wouldn't do me much good. Wouldn't do you much good if I gave you bad examples. All right, so that's it. That's how you do that. One more page, and we're actually almost done. So we're getting to be the half-hour mark. Oh boy, one more page. That's it, huh? So what must be true about a circuit? And I'm going to put out that there's at least two things. Well, both are equally important. For it to work properly, the most important thing is that it's an actual circuit. It has to be, it's a complete circuit with no breaks. In other words, you have to have a complete solid loop. There's no breaks. There's no open parts of the current of the circuit. All right. I would also argue that it has to have a voltage source. You have to have something voltage. You have to have something that pushes the battery or pushes the electrons, and usually it's a battery. So that would be, but this first thing is the most important thing. In order for it to work properly, you have to complete loop. All right. In fact, I'm going to, in parentheses here, that means a loop. Okay, a closed loop for the electricity to go around. Why must all circuits contain a voltage source as a battery? Well, I kind of just mentioned that. Something, and I'm paraphrasing or I'm summarizing or whatever, but use your own words here. The idea here is something needs to push the electrons, to push the charges or electrons. Without the battery or any kind of a voltage source, the electrons are just going to sit there. And so that's what the battery does. So something needs to push the electrons, and that's what the battery does. So what directions do electrons flow in a circuit, and why? And I'm going to kind of draw a picture here of a battery, and I'm going to have a positive end and a negative end. So I'm going to have my negative end here and my positive end here, and I'm just going to draw a little wire. And then I'm going to indicate the direction of the flow of charges. And that's a terrible arrow, but okay, kind of works. So the flow of charges, when it comes to, I should say the flow of electrons flow from the negative end to the positive end. Why? I mean, electrons repel each other, and they're attracted to the positive side. That's why. I can't, I'm not going to write all that down, but just understand that they're being squished together over here. They're being forced together, and they're all repelling each other, and they hate each other, and they just want to get away, and so they leave as soon as you connect a conductor, something that they can move through, and so they move through it. And where do they move to? Well, they move to a place where they can spread out, and there's plenty of room over here until, you know, the chemical reaction pushes them to the other side. So that's why. All right. Relationships. What happens to the current when more light bulbs are added to a circuit in series? And why? We talked about this today, but just to recap, in series it gets dimmer. Hang on, the current. What happens to the current? Less current. The current decreases, which would cause a light to get dimmer. Why? because as you add things in series, that's just adding more and more things that the electricity has to go through. And so when you add more and more things that the electricity has to go through, you're adding more resistance. Resist. What I get for talking and trying to write at the same time. It doesn't work. So there's less current because there's more resistance. And because there's less current, you're going to have dimmer light bulbs. What happens to the current when more light bulbs are added to a circuit in parallel? I think there might be a typo somewhere around here where I meant to say, I screwed it up and it said series. So just kind of be careful. Look at these words here. One of these is wrong. And I think it's actually that third one that's going to be a typo on your copy. I apologize about that. I'll just make sure. Okay. So what happens to when they're added in parallel? Well, actually, there's going to be, how do I say this? More overall current. But the individual light bulbs are unaffected. Individual bulbs are unaffected. And the reason why, it's because there's more options. Because more options, I guess. Because there's more, there's more pathways for the electrons to take. I'll just kind of summarize it that is because there's more pathways. I'm trying to summarize it in as few words as possible for you to get the big idea that there's more pathways, there's more choices. Like I said, if a few people needed to go from my room to the cafeteria, that's fine. And then if like a couple more people said they needed to go to the auditorium, that's fine too. Now we have more people moving. The people going to the cafeteria are not affected by the people going to the auditorium, but there's more people in the halls. And then if somebody else, 3 other people, and said they need to go to the library, well, now you have more people in the halls, so you have more overall current, but the people going to the cafeteria, the people going to the auditorium are not affected by the people going to the library. You see what I mean? There's more pathways available. So the individual pathways are not affected, but overall there's more current because that's just because there's more pathways. And 2 more. And we're just over the half-hour mark, so we're doing pretty good. What happens to the brightness of the bulbs when more are added to a circuit in parallel? Well, so the other questions we're asking about current, and now this one's asking about brightness. So let me switch colors just for fun. Let's do, ooh, how does orange look? Nah, let's not do orange. Orange never looks good. Dang it. I'm kind of, all right, we'll just do red. So what happens to the brightness? Yeah, that's a huge difference. Whatever. When they're added in parallel. Because of that, when they're added in parallel, nothing. Okay? Nothing happens. Because of the reason I said before. Okay? And I'm just going to put ... because I explained it already, is that you have, you just have just some, how do I say this? You have more options, and so nothing's going to happen. So, actually, hey, wait a minute, Mr. Jern, I did not make a typo. This is silly. Because look I'm about to answer this question in the last. What am I thinking? So this actually does say series, and it should say series. And so this answer is wrong because I'm about to answer that question. So if you add more light bulbs in series, the brightness actually gets dimmer. And why? Because, well, I answered that up above. It's the same answer as before. There's less current because there's more resistance. And so since there's less current, you're going to add more and more things. Like if we all had to go to the cafeteria, and then we all had to go to the auditorium, and then we all had to go to the library, it's going to be just a big old production, and there's so many stops we have to make. And every time we make a stop, we all got to slow down, and it just slows everything down. And that's what's going on with the electrons. You know, it's like, you got more and more things added to the list, you're going to have to get, the electricity slows down. You get less current. And so things are going to get dimmer. Okay, the last question, why do bulbs connecting voltages in parallel not get dimmer? That's what I was talking about before. There's more pathways. They're just not affected by each other. All right. So I'm going to call it in a second, unless I don't see any last minute questions here. So we will talk tomorrow, and I'm going to put this back up just briefly, so you can pause it there if you want to, if you're watching this on YouTube. And like I said, let me know if you have questions, and we'll be good. So just study this stuff, and you'll be good. Good night.